Hello again, everyone. We're back for lecture 2 of our course 2ME301. This is about quantitative methods. Still, this is part 2, because we're basically picking up where we stopped from the previous lecture. We're going to talk a little bit more about basic statistics, a little bit more about the common types of experiments and studies that you can do, and go into a bit more details about some of the stuff that we have already seen with some more examples and some more explanations also. So we start by doing a quick recap of where we were before. So we talked about media technology and design thinking. So we talked about how doing research in media technology can be considered as a way of doing design, or a way of applying design thinking, right? Design thinking is a very broad, very general concept. It can include many different things, but for media technology, it's constrained to, let's say, solve user-centered problems through the novel design of media-based solutions, right? There's some constraints inside the idea of design thinking that when applied to media technology. And of course, as we discussed, the research itself encompasses all the steps from empathizing to defining the problems, ideating, prototyping, and testing. But in this specific course, we're talking about the actual testing in this framework. So we're talking about having something. Well, of course, it starts from the proposal and everything, but this lecture specifically is about, like, okay, what do I do after I have this thing, and I need to somehow evaluate whether it actually works or not. And using quantitative methods means basically analyzing data, right? Gathering data from this process of the evaluation that you're running, and then analyzing that data, right? So very quickly we talked about what is data. I mean, data, right? This is such an abstract and open word, but for us, what do we consider as being data, right? So in the simplest possible way, and in order to begin our journey, we decided that we would focus only on one set of measurements. Some of you have decided to go for two sets of measurements in your data gathering process, which is perfectly fine. We will get there. But in order to take one step at a time, we're starting with one set of measurements. And as an example, I'm showing here, let's say, a picture of the times that it took for me to bike from home to LNU during August 2018. These are, I measured this, I'm not sure if I measured it every day, not every day, because I have what, 22 measurements. So I guess, yeah, I mean, I probably worked around 22 days on all of those. So I'm guessing these are all of them. And the thing is that what we talked about when we were talking about data was that in order to be interesting statistically, data needs to have variance, right, or variability. It makes no sense for us to analyze a data set that's composed basically of the same thing repeated over and over again, because if that is the case, then you already have your answer, right? The answer is that value that repeats itself over and over again. You don't need to do any statistical data analysis on that. So an interesting, a complex enough question involves data that has a variability, because then it becomes the question of, like, what is the answer to this? I mean, I have this data and I've gathered it, but what is the answer that I can take away from this data? And if you don't have variance, then that means nothing, right? And what you see here is this thing called a histogram. I'm not sure how many of you are actually familiar with a histogram, but the histogram basically shows the distribution of the data, right? This is a visualization. It's not the only type of histogram that you can do, and it's definitely not the final, solution to visualizing the distribution of the data, but it's one way of visualizing the distribution. And by visualizing the distribution, you get like an overall picture of how the data looks like. The histogram is probably the most common one. And in a bit more details, how exactly is it that you should create and interpret a histogram, right? Why is it that this shows the data distribution? Well, first of all, there are some bins, or sometimes we call them buckets, that are along the x-axis. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 buckets. They go from 26 to 30.5, which is more or less the, let's say, the range of the data that I gathered. And what you see in the y-axis here, let's say the heights of the bars, are the value counts. Sometimes they're probabilities also. You can see probabilities here, like 10%, 20%, 30%, and so on. Basically, they're the same. It's just that a probability is showing you a relative value, like relative to the total, right? So for example, in this case, since we have 22 data points, then here, instead of 1, you would see the probability that is equivalent to 1 divided by 22. So 1 part of 22. Then this would be like 2 parts of 22, 3 parts of 22, 4 parts of 22, and so on. And 7 of 22 is almost 1/3. So here you would see something that would be almost a third. So almost 33%, let's say, of probability. Like I said, the shape is the same. The only thing that would change would be the values that you see here. And whether you use one or the other depends on the kind of data that you're analyzing and what you want to show. If what you want to present is related to probability, then you can show probabilities here. The distribution stays the same. So basically here what you see is the counts of values inside each bucket. 2 values in this bucket, no values in this bucket actually, so this bucket is empty. There are no values between 26 and 26.5 in my data set. There are 2 values between 26.5 and 27 in my data set. There are, again, 2 values between 27 and 27.5. Then there are 4 values between 27.5 and 28. And there are 7 values between 28 and 28.5. So this bucket obviously is the one that has the most values. So most values fall in the range between 28 and 28.5. Well, not most. If I say most values, it kind of feels like more than half of the values we here. But related to the other buckets, this is the one that has the most points, right? Though it's a little bit less than a third. So it's basically that's how the distribution here comes. So it's, in a way, you could see it that it shows the density of the data, so to speak, around certain areas, right? And this will basically give you a rough overview of how your data is distributed. And from this, you can make some decisions or understand better how your data, what kinds of things you can do to your data, because different distributions kind of tell you different things about it. So this is one of the, let's say, easiest things that you can do in order to visualize your data distribution when it comes to one variable. So by one variable, I mean one set of data, one set of measurements. But the question that, like, if this was a research question, my research question would not be, how does the distribution of values look? That's not the kind of research question that you ask yourself, because that's very subjective. Right? I mean, how does the distribution look? Well, for example, if you change the bucket size here, instead of going from 26.5 to 27, I went, for example, from 26.5 to 26.6, and then from 26.7, 26.8, so on and so forth. Then the buckets will be thinner, and there will be less values in each of the buckets, and that would change the visualization, right? So I can't ask in my research question, how is it that the distribution of the data look like? That's not a statistical question. That's not a research question. You can use the histogram to present your data, but not to answer your research question. Your research question, our research question in this case would be, for example, how long did it take for me to bike from home to LNU during August 2018? And one possible answer to that would be around 28.31 minutes. And I guess you're guessing that this is the average. So if you look around here, you can see that since most values are in this region here, and this is more or less symmetric, then you would expect that the average would be somewhere over here. And you would be right, because that is the average, 28.31 minutes. So like I said, that's one way of answering these kinds of questions, right? You will have other kinds of questions, like how long does it take to do this, how long does it take to do that, or how many people go through this place every day, or how much money do certain people make, or something. You ask a question, and you want to answer that question with one value. You want an objective answer to that question, right? So visualizing the distribution is nice, but to perform research, we need more objective ways to describe and compare distribution. So if I want to compare two different things, I cannot compare them simply by looking at the distribution and saying, well, yeah, this one looks a little bit, let's say, thinner than this one, or whatever like that. No, you need values. You need to say, this one, the mean of this one is X, the mean of this one is Y. And that's why we use the mean. So the mean is the most, it is by far the most common, right? Descriptive statistic of a distribution. And if you do need to describe your data distribution with one value, this is it. But please always keep in mind that by doing this, you're obviously losing a lot of information in terms of exactly how your distribution looks, right? The shape of the distribution is being lost. That's it. But you have to do this. That's how you answer a research question initially, as we will see. The formula for the mean, although you probably don't need to know that very well because you have mean in every statistical package that you could find, but the formula is simply a sum of all the values, like x1 plus x2 plus xn until you get to the final one. That's what this thing is, I guess you know it. The sum of xi between 1 and n, and then you divide it by n. So you sum everything, and then you divide by the number of the values. And I guess you know that, but you don't really have to care because you will. This spreadsheet is in every statistic package. But it's interesting to know, like to reason about it when you're using it. And these are a few different distributions and where their mean stays, or where their mean lies. And it's very interesting to see how the mean can be very representative or very informative for some distributions, but not for others. Like for example, this is what we call a normal distribution. I will talk more about the normal distribution in a few minutes, but a normal distribution is this symmetrically shaped bell curve, as you say. It looks like a bell, kind of like a wide bell, but still a little bit like a bell. It goes up and then it goes down. And when your distribution is normal, when you take your data, you plot it, you make a histogram, and you see the shape of a normal distribution, that gives you a very good confidence that the mean actually represents the distribution very well. It's one of the, say, characteristics of the normal distribution. The mean is actually very representative because you really know what it means. It can be a very important part of term, let's say, the distribution. Now, when you have a skewed distribution, for example, like this one, what does it mean that it's skewed? Skewed means that it's not symmetric. It is different to the left-hand side than it is to the right-hand side. one of the sides is more steep, goes up very quickly. The other side goes down very slowly. There are many distributions like this, both to the right and to the left. So when most values, for example, in this case, most values are, well, let's say there are not many values that are very small, then they become, then there's a lot of values that are, let's say, small but not super small, and then it goes down very slowly because the values, as the values get higher, they get slowly and slowly less frequent, let's say. And this is sometimes distribution, for example, of salaries, depending on the country. The different countries have different distributions, but for example, you may have a country where there aren't that many like very small salaries, so you wouldn't expect someone to make $100 or $200 a month. But then it goes up very quickly because most people have smallish salaries depending on the country they are. For example, in a third world country, you would expect that most people would have very small salaries, but not super small as such that they can eat. So it goes up very quickly up to a certain point where the, let's say, the common range is, and then it goes down slowly because there are less and less people that are very rich, right? So when it comes to the end, then there are very few people who are very rich, but there's still quite a lot of people that can make more than the average. But as you can see, one interesting thing about the skew distribution is that if you take the average, it doesn't really lie in the exact point where you may think that it should lie, like for example at this point here. So it doesn't show, let's just put it this way, the average is not the peak of the distribution, right? The peak is one thing, the average is something else. So the average is skewed to the right. So when if you know that so you see how interesting it is to have these two different bits of information at the same time. You have the shape of the distribution by seeing it, by looking at it, and you have the mean. And by basically confronting these two things, you can have a good idea of whether the mean is actually representative or not. Because in this case, you may think that it's actually not that representative. So you would, for example, if you knew that your distribution was skewed, you could adjust it a little bit to the left so that you could find the peak or something like this. So you would expect it in a different way. For a uniform distribution, it's just a distribution where most values are basically similar, right? So that's called uniform because it represents a uniform probability distribution. So every value has the same chance of happening, so to speak, or roughly the same chance. And in this case, of course, that mean actually means something because it's so uniform that you don't really need the mean so much. Every probability is just the same. And in the case of the irregular distribution like this one, where you have many peaks and valleys, many peaks, valleys, peak and valley, then the mean doesn't really mean anything. You take the mean or the average, and that gives you some number, but when you look at the distribution, it's so irregular that, like, what is that telling you about the peak? Nothing. Because there are so many values around the mean anyway. Most values are somewhere else completely. So you would need, like, I don't know, 3 or 4 different numbers here in order to show each of the peaks and to show each of the most populated areas here in order to actually have an information, so to speak, about the distribution of the data set. So, I mean, we still use it, right? We still extract it because we don't expect that so many distributions will be irregular like this, or else we would do it. There are reasons to believe or to expect that well-measured data should not look like this. This is usually a combination of different measurements done at the same time in a, let's say, not careful way, because there seems to be like there are too many things to measure at the same time. So it could be, but it could be that the data simply irregular. So in that case, you can't really rely on the mean that much. So you see again how it's important that you can have look at the mean, but also look at the distribution, so that you can actually have a little bit of information on whether your mean actually means anything or not. Now, this is also very interesting. This is a comparison between the values that I got on August and the values that I got on November for the same thing, right? So still for cycling through from my home to Alan. In November, it was much colder, and sometimes I didn't even take the bike because I decided to take the bus. And you can see that it's much more irregular. So depending on the weather, depending on whether depending on many things, it took me all the way from around 24 minutes to 32 or 30. And I don't know. I guess some other stuff happened here that maybe I don't know. So maybe I stopped to buy something somewhere. I don't know. But the thing is that these are very different distributions, but they have the same mean actually. And of course, as you can see, because they have the same mean, these are actually not super real data, as you might have expected. I played with it a little bit so that it could show it would have the same mean, but with different distributions. Although this is more or less based on real data. But what matters here is that what I wanted to tell you is that don't trust completely only on the mean of your data, because again, very different distributions can have the same mean and will, or at least very similar means. But when you look at distributions, you see completely different pictures, and that's something that's important. So always, not always, but as always when it's possible, use a histogram or show a histogram together with your, so that you can have more information on it. Now, one interesting thing is think about, like, okay, the mean is 28 by 31 minutes, right? I have a rough value that describes my data, and it gives you one objective answer to the question. But really, considering that this is one value that is supposed to represent 22, I think it would be reasonable to expect that at some point you would ask yourself, are you sure? Like, how sure are you, or how much can I trust this 28 by 31 thing? Like, is it really representative? So we looked at all the distributions, and we saw that in some cases, the mean is very informative. In some cases, the mean is not very informative, right? So it makes sense to ask, how informative or how clear is it that this mean is actually a good representation for the entire data set? So one thing that usually follows the reporting of the mean is the reporting of the standard deviation, or sigma, which as it is usually known. Now, this also comes from data itself. It's also a measurement like the mean. It's also one value, but instead of representing, let's say, trend of your data, or being like a substitute for the data set, it actually gives you an idea of how much that data set varies. So you can think about the standard deviation as a measure of error. How wrong is your mean? How much, or the intuition as I put it here, how far away are the points from the mean on average? So, okay, I have a mean, right? And I give you my mean, but at the same time, I measure how far away on average all the values of my set are from the mean. So if the standard deviation is very small, then that means that in general, the data points are not too far away from the mean, right? They gotta stay close to the mean. So the mean is good. So the smaller the standard deviation, the better is your mean at representing your data set. Because basically saying, well, the data set actually doesn't vary too much around it. So the mean is good. Right? This is a very, very like formal intuition. We're gonna discuss exactly how this is used, but that's in a very informal intuition. You can think of the smaller standard deviation, the more informative your mean is. So this again is the formula for computing sigma. And again, usually you don't need this because this is in every spreadsheet, every statistics software. But it's good to have an intuition. It's good to understand how it works so that you can reason about what you do, right? And you know how to use this correctly. So basically, you can see here that this thing here is the mean, right? It's the mu, which we saw before. I forgot to say the letter, sorry, but letter for mean is mu. Now, basically what we're doing here is, okay, we take every data point, we take the distance of that data point to the mean, or the error of that data point to the mean. And we sum, but we sum the square of this value. Then we divide that again by the n, because remember that the mean, when you compute the mean or the average, you have to divide by the number of points that you're computing. And since here you're computing the average error, so you still need to divide by n because you compute like n errors, and now you divide by the mean. And since you squared it, then you have to take the square root in order to, let's say, undo the square. And this is usually how you do it, especially because when you square it, it's positive. So the standard deviation is always positive. It doesn't matter the signs of these values. It doesn't matter if x is less or more than the mean or anything like that. It will always be a positive value because you squared it and then you took the square root. That makes it like, that's like a way to make sure that whatever value you have is actually positive. And it's never negative. So you square it, then you take the square root, and then it becomes positive, even if it was negative. Okay. And that's because we don't care whether it's negative or positive. All we care is just the magnitude of the value, right? All we care is just how big it is. Whether it's small, negative or positive, it doesn't matter. So this gives you then an idea of error, how correct or how informative my mean is. So on average, how much the points are varying around the mean. And that is very, very informative, very nice. And this pair of sigma plus, let's say mu plus sigma, if you put them both together, they are usually very informative, and they are usually a very good way for you to report on the shape of your data without actually having to show the actual visualization of the data. Even though you can show the visualization, but like we said before, when you're answering a research question, you need to be objective. And one very objective way to answer a research question is to have mu and sigma at the same time. Now, this is a very simple example of why this is so important to have this sigma value and how much it adds to the representation of the data. So, for example, let's say this is a river, right? Like a cut of, let's say, the river. And you may ask yourself, how deep is this river? It's just a simple question. How deep is this river? Now, of course, how deep is this river is not a question that has one answer, because the river is deep, it is different, the depth is different in different places of the river, right? So you can't just say it's this or that. So you could say, for example, the average depth of this river is 4 feet, and it is actually. If you take this plus this plus this plus this plus this plus this plus this, and then divide it by 7, you will get 4. So you could just, if someone asks you like, what's the average depth of this river? Then you could simply say, well, you know what? It's 4 feet deep. And the person might say, okay, nice. I'm afraid of deep rivers, but 4 feet is actually not that deep. So I'm gonna swim on this river based on, I make a decision to swim in this river based on the answer that you gave me, that it's 4 feet. 4 feet. on average. Was that a good decision? If this person is afraid of swimming in it, actually maybe not, because if you compute the standard deviation here, and this is dividing by n minus 1, but please ignore this, we're going to come back to this later. But the standard deviation here is found to be 3.55. So basically, this river is indeed on average 4 feet deep, but the standard deviation is almost the same as the average. So on average, the points differ from the average almost one full average, right? So that's a lot of standard deviation. That's a very large standard deviation considering the average value. It could go all the way from 0.5 or half a feet to 7.55 feet on average, right? And as you can see in the distribution or in the picture itself, it actually goes down to 10 at some point. So this is completely, if you don't really report on the standard deviation at the same time that you're reporting on the average, then it becomes very, very hard to understand really how your data looks like, and to make, let's say, a good informed decision. So this example comes from this website, which has some easy to understand ideas about statistics and so on. So again, if we go back to that quasi-real data that I showed you before about my bikings from August and my bikings from November 2018, which happened to be a little bit before I offered this course for the first time, you can see that the standard deviation for this one is 0.86, and the standard deviation for this one is actually 2.20. So if I took two different data sets and they had very similar means, but I looked at their standard deviation and I saw that the standard deviation of one was actually much larger than the other one, that would give me a good base of comparison. That would give me a good information about how these two distributions are different, even though they may have the same or almost the same mean. So again, just to reinforce the fact that pairing the mean with the standard deviation actually gives you a very nice view of the data, much better than just looking at the mean.